So we're going to talk about counting principles today. So what we're going to do is we'll talk about counting, and towards the end of the lesson we'll make a connection between what we're talking about today and the binomial theorem. Why we're talking about counting the binomial theorem. What we talk about today is not on the quiz.
Is it super easy?
It's relatively easy, yes.
Can it be on the quiz then?
All right.
Is it relatively easy?
I want to start with an example. So what we're talking about is counting things that can be difficult to just write down and count one by one. So let's say a typical problem that has to do with counting. Next time, in next class, we'll talk about probability, counting and probability. Is we have an urn. An urn, like a big flower pot, and it has ashes, I guess. And it contains, inside this urn is balls numbered 1 through 6. So like the lotto thing, sort of. All right, so what we're going to do is we're going to pick one. We're going to write down the number. We're going to put it back and then draw another one. Pick another and write down the number again. What we want to know here is how many ways to get a total of 8. So we add the two numbers together, and we want to get a total of 8. Well, what are the different ways that we could get an 8 with balls numbered 1 through 6? 2 and 6. 3 and 5. 4 and 4. Right, we could get them in a different order. 5 and 3. And then a 6 and 2. All right. So we get 5 ways. So in this example, it's not too bad just to write them down and count. We call this type of situation where we pick something and then we put it back so we can pick it again. We call this a choice or counting with replacement. And this will come, you'll see this when you talk about different ways you can pick cards out of a deck. Depends on whether you put the card that you pick back or not. All right, so now we're going to do the same thing, but we're not going to put the ball back. And we're asking the same question. How many do we get a total? How many ways can we get a total of 8? Well, what's going to change?
Can't do 4 and 4.
We can't get a 4 and a 4. Because once we pull the 4 out, it doesn't go back in. So we can't get 4, 4. So our total is 4 ways. We call this counting or choosing without replacement. And it'll be important, as we saw in this example, to decide whether or not we're counting or choosing with replacement or without replacement. And what we're going to be interested in is counting things that are a little more complicated than just if we have 6 things to choose from. So one of the ways that we're going to do that is called the fundamental counting principle. Everybody good with the idea of with and without replacement?
Yeah.
We have used the fundamental counting principle, just we haven't made it formal. In counting, in probability, we call something that happens or something that we can do an event. So one event can happen M ways. You have 5 shirts. Another event can happen N ways. You have 3 pairs of pants that go with those 5 shirts. Together, they can happen M times N ways. So with our 5 shirts and 3 pairs of pants that go with them, we could make 15 outfits. And this, we can extend this to more than 2 events. So what we do to count in those situations is we multiply the number of ways one event can happen by the number of another event, et cetera, et cetera. So if you go to buy a pizza, you can get 3 different kinds of crust and however many different kinds of toppings and however many different kinds of cheese. You multiply all those things together to figure out the number of different ways you could make a pizza. All right, so let's look at a couple of examples of the fundamental counting principle. Let's say we want to make a PIN number or a password. So then our password's not going to be very good. We want a 3-letter PIN. And I'm going to say with repeats. So how many letters can we pick for the first letter? 26. 26 letters in the alphabet. How many can we pick if we're allowing repeats? Times 26 times 26. So that gives us 17,576 different 3-letter pins. That seems like a lot, but since we have computers can calculate all those 17,000 pins very quickly. What if we wanted not to have repeated letters? Without repeats. 26 times, we have how many choice for the second? 25 times 24. And if we calculate that out, 26 times 25 times 24, that comes out to be 15,600. So quite a few less without repeats. What if we wanted to make without repeats with all the letters of the alphabet? So how many choices do we have for the first letter? 26 times for the second letter without repeats? 25, right? Times, how many do we have for the third letter if we're not repeating? 24 times, how far does this go down? All the way to 1, which is 26 factorial. So if we don't have repeats and we are allowing all the letters, we get 26 factorial. And this idea of the 26 factorial is going to come into play with the next thing we talk about. All right, so everybody good with the fundamental accounting principle? All right, so the next more complicated situation is we're going to pick a certain number of things out of a larger group of things. And we want to know how many ways we can do that. So the first way that we are going to talk about doing that is a permutation. A permutation is an ordering, and this ordering is important, of R things out of a group of N things. And I say ordering because in permutations, order matters. And a permutation, the way we calculate a permutation, is we write the symbol as NPR, is N factorial. That's how many ways that we could arrange all of the big group of things. But we want to divide out the ones that aren't the orders that we're interested in. So we have to divide by N minus R factorial. And for permutations, we're going to have some reason that order is important. We want to know how many different ways a group of 10 people could finish first, second, and third. So a different person finishes first. That makes a different thing, even though it could be the same 3 people finishing in the top 3. If a different person finishes first, it's a different thing than if person number 2 finishes first. You might have a committee, and you want a president, vice president, secretary. It's a different committee if person number 2 is a president instead of person number 1. That makes it different. So the order matters. All right, so let's look at an example. Let's use the example I gave. So we want a president, a vice president, and a treasurer out of a class of of 35. So this gives us some information about how we want to order these 3 things. We want it in the order president, vice president, secretary, or treasurer, sorry. So if this is 1, 2, 3, that's different than if the president, vice president, and treasurer are 3, 2, 1, even though it's the same people. So the order matters. So I'm going to say order matters. So this is a permutation. And what we're going to calculate here is 35 P3. So we have 3 things that we're picking. So that's going to be 35 factorial over 35 minus 3 factorial. We know how to do this by hand. So let me show you in your calculator how we can calculate permutations. I'm going to do 35. I'm going to go to math just like I did for the binomial coefficient. Arrow over to probability. NPR, the permutation, is number 2. So I'm going to do number 2. And we're picking 3 things. And that is 39,270. So that's a lot of committees with a president, vice president, and a treasurer out of a class of 35. That's a lot of, and it would be really difficult to write down all the different 3-person permutations of president, vice president, and secretary out of a class of 35 and count them up. All right, questions there? Now, I want to look at another example that's similar to the one we did before with all the letters of the alphabet, how many different ways we could arrange them. That one turns out it is a permutation because we have a specific letter that's first, a specific letter that's second, specific letter that's third. But what if we wanted to arrange how many different ways we want to arrange these letters in the word mathematics? So what's the problem here? What makes us different than just arranging the letters of the alphabet? We have some repeats. So we have to take into account the repeats. So what we call this is the number of distinguishable permutations. Because if we put one M and then the other M, it's the same as if we put the second M and the first M in the same 2 places. Those 2 aren't distinguishable. So we have to take into account that. We also have 2 A's and 2 T's. So in general, we have N objects. Our distinguishable permutations are N factorial, just like the example we did with the alphabet, where we have 26 factorial. But we have to get rid of those permutations where the 2 M's are interchanged. So we're going to divide by N sub 1 factorial times N sub 2 factorial, N sub 3 factorial, dot, 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 to N sub k factorial. And this is how many of that particular letter we have. And the N sub 2 would be if we have a second repeat. And the N sub 3 is if we have a third repeat. And the N sub, we go all the way, we count all the different repeats that we have. And N is all of these added together. N sub 1 plus N sub 2 plus dot, 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 plus N sub k. So in our example, how many total letters do we have?
8.
No, just counting them all up. 11, right? So we would have 11 factorial divided by, we want to get rid of the arrangements where the M's switch order? Well, we have two m's, so we're going to divide by 2 factorial. We have two a's, so we can switch the places in those. So we're going to divide by 2 factorial. And we have two t's, so we're going to divide by 2 factorial for the t's. So this is for the m's, this is for the a's, and this is for the t's. And the rest, we just have one of. Well, what's 1 factorial? 1. So if we could write that out, 1 factorial for the h's, 1 factorial for the e's. So we'd have, let's see, 2, 4, 6, 7, 8, 9, 10, 11. That's just 1, because those don't repeat. And we calculate this out, and we get 4,989,600. So that's still a lot of arrangements of those letters that are distinguishable. So we just take the total number of letters we have, factorial, and then we divide by the number of repeats, factorial, for each repeat that we have. And this takes into account the 2 m's that we could switch places, the 2 a's that could switch places, and the 2 t's that could switch places. Yeah.
I don't understand the ones.
Those are just one, since these letters, since the h doesn't repeat, we just have a 1 factorial for the h. Since the e doesn't repeat, we have a 1. We could leave that out, but just so it matches the formula, I kept all the pieces in. So really, you only have to include the ones that repeat, because the rest is just 1. All right, questions there? This doesn't come up quite, I'll say not nearly as much as permutations. The other counting method that we're going to use to tie this back into what we talked about with the binomial theorem is combinations. Combinations are a grouping of R things out of a group of N things. And we said a grouping. I say a grouping because order does not matter. So, for example, a combination might be your toppings on a pizza. A pepperoni sausage and mushroom is the same as a mushroom sausage pepperoni pizza. They're the same thing. A BLT is the same as a TLB. Now, culinarily, that might not be true, because I would argue that when you make a sandwich, the mustard has to go on the bread that goes on the top. The mustard doesn't go on the bottom. That's a different thing. It's not right otherwise. The cheese has to go on the top, not on the bottom. So mathematically they're the same, but in terms of eating them, they're different. So a sundae that you make with ice cream, hot fudge, and nuts is the same as one that you make with nuts, hot fudge, and ice cream. Now, when you eat them, they might be different, but mathematically, they're the same thing. All right, and you never make a peanut butter sandwich on a hamburger bun. That's just wrong. Yeah. Oh, it's terrible. It's terrible. And you never put the top of the hamburger bun on the bottom. That's wrong. All right, so our combinations. NCR. Does this look familiar? Those are the binomial coefficients. So the binomial coefficients are the same as the number of combinations of taking n things r at a time. So binomial coefficients and combinations are the same thing. So that's an interesting connection. And here order doesn't matter. So for example, we might just want to, instead of a president, a vice president, and a treasurer, we might just want to find a 3-person committee. From a class of 35. How many 3-person committees can we make from a class of 35? It's not, here order doesn't matter, because a committee with person 1, 2, 3 is the same as a committee with person 3, 2, 1. There's nothing that orders those people in any kind of ranking. All right, so this is, I'm going to say order doesn't matter. So this is a combination. So this is going to be 35C3, which is 35 factorial over 3 factorial times 35 minus 3 factorial. And notice the difference between this, the combination, and the permutation is this 3 factorial on the bottom. The 3 factorial counts up how many different ways that we can arrange those 3 people in a group. 1, 2, 3, 3, 2, 1, 1, 3, 2. So we're getting rid of that possibility. And I'm going to go to my calculator. I'm going to do 35. Go to math, over to probability. Do number 3. And this is 3. And we get 65, 45. So quite a few less combinations than permutations. Permutations and combinations are the more common counting techniques that we're going to use when we get to probability. And we need to count in order to find probabilities. All right, questions? All right, there we go.